If we were living in a computer simulation, would we be able to tell? This is a question that is quite difficult to answer. However, physicist Melvin Vopson from the University of Portsmouth in the UK suggests in his newly published paper that he may have found a clue. The simulation theory first gained public attention with the release of The Matrix in 1999. But it wasn't until philosopher Nick Bostrom's 2003 paper that the idea began to be taken seriously by the scientific community. Bostrom systematically argued that we might be living inside a simulation designed by an advanced civilization. Since then, many researchers have explored how this idea might be tested. Now, Vopson claims he is more confident than ever and states, just as computers aim to save memory and operate more efficiently by compressing data, the universe might be functioning in the same way. This gives gravity a different interpretation, not just as a physical force, but as a result of the universe's effort to maintain internal order. This perspective stands out as one of the most intriguing ideas to follow the popularity of the render hypothesis in the 2020s. Moreover, the paper was published in a peer-reviewed journal by the American Institute of Physics, meaning that the mathematical models it presents have undergone scientific scrutiny. Of course, this doesn't imply that the theory represents reality itself, but it does provide a solid theoretical foundation. Nearly all foundational assumptions of simulation theory rely on an information-based interpretation of the second law of thermodynamics. Today, many physicists consider entropy not just in terms of energy, but also in relation to information. To fully understand the paper, we must now take a closer look at how the second law connects with information. The second law of thermodynamics states, in a closed system, every natural process increases the total entropy of that system. What does this mean? For example, a hot cup of tea in a room gradually cools down because it releases heat to its surroundings. It does not spontaneously reheat. This reflects the tendency of energy to disperse from areas of high concentration to low, leading the system toward greater disorder. To illustrate, before the tea enters the room's entropy is 1, and the tea's is 0.5. As the tea cools, its entropy drops to 0.4, while the room's rises to 1.12. When combined, the total entropy of the system becomes 1.5112. That is, from an energy perspective, the system's entropy has increased and overall disorder has grown. The core concept of simulation theory, information entropy, was first introduced by Claude Shannon. Shannon developed a mathematical framework to measure how much information a message contains, in other words, how much uncertainty it eliminates. Ultimately, we use Shannon's entropy equations to determine whether an event increases or decreases information entropy. In 2022, Melvin Vopson reinterpreted the second law of thermodynamics in terms of information entropy. According to him, while classical entropy inevitably increases over time, information entropy doesn't necessarily follow the same rule. In closed systems, the amount of information may remain constant or even decrease. So in the tea example, while energy-based entropy increases, the information structure of the system might actually become more ordered. Vopson explains it this way. The universe might behave like a computer. Computers compress and reorganize data to reduce memory usage. That's where simulation theory and thermodynamics intersect. Yet, for Vopson, this process doesn't require a literal processor. It may simply be embedded in the nature of the universe itself. He compares it to saving a file in .zip format instead of .txt. The content stays the same, but the storage becomes more efficient. It's important to note, this new paper is not experimental. It's entirely theoretical and mathematical. And we know that a mathematically consistent model does not necessarily reflect physical reality. In this work, Vopson makes a striking claim. The universe might behave like a computer, and gravity could be a consequence of the universe's effort to keep information organized. What does this mean, and how is it explained? Vopson starts with the idea that physical laws might actually be encoded structures. If it can be shown mathematically that these laws are equivalent to a set of information processing rules, then it would provide strong support for the simulation hypothesis. In this context, physics might not just describe nature, but also reveal an underlying system of data organization. Vopson proposes a simple but effective model. He imagines the universe as a flat, two-dimensional grid composed of 10 by 10 squares. Each square is an information cell. If it's empty, it holds a value of 0. If it contains matter, it's marked as 1. In other words, every point in the universe digitally encodes whether it contains matter. These units are referred to as Planck cells, and this concept aligns with ideas like black hole entropy and the holographic principle. Initially, the grid is empty, and the system's information entropy is 0. All cells are 0, carrying no informational content. Then, four particles are randomly placed into different squares, each now holding a 1. The system becomes more complex, randomness and information density increase. At this stage, Vopson calculates the system's information entropy. At first glance, one might assume 4 bits, since 4 cells are marked 1. But in Shannon's model, not only the quantity, but the distribution of information matters. Whether the filled cells are near or far, clustered or scattered, affects the entropy calculation. Based on this, the system's entropy is computed to be 2.77 bits, a jump from the initial 0. Now enters Vopson's second law of information dynamics. Information entropy must decrease. To achieve this, the particles move and converge at the center of mass. Instead of occupying separate cells, they unite in one. The result is a more ordered system requiring less information to describe. When entropy is recalculated, it has dropped to 1.38 bits. The mass remains the same, but the system's informational complexity has significantly declined. To contextualize this, we can look at the ACE experiment conducted at ISIS in 2010. Researchers observed how microscopic particles suspended in fluid spontaneously formed crystal-like structures in microgravity without any external force. In other words, the particles tended to organize themselves into central clusters, echoing the behavior seen in Vopson's model, where 4-1s gradually converge into a single information cell. Now things get more complex. We turn to the concept of an information-based force. Dutch physicist Erik Verland, in 2011, proposed that gravity is not a fundamental force, but an entropic effect. He argued that the attraction between objects arises from changes in the system's information entropy. This was a bold and imaginative shift in thinking, and it marked one of the first major efforts to unite thermodynamics, information theory, and gravity. Returning to Vopson's model, the system begins at 2.77 bits and drops to 1.38 bits. This decrease reflects the universe's drive to reduce informational redundancy. The process manifests as an internal force drawing particles toward the center, a drive for more efficient information representation. Although not explicitly stated in the paper, an implicit assumption is that the universe constantly behaves like a processor seeking optimal configurations. Arguably, the model also suggests that running such a simulation would require a far more powerful computational infrastructure than previously imagined. The shift toward lower entropy is framed as a form of optimization. Initially, the scattered particles increase the system's entropy due to diverse positions and energy states. But as they move and unify at the center, a single cell can represent the entire mass, reducing informational overhead. Vopson interprets this as a kind of digital efficiency. Fewer cells, more representation. He sees the convergence of particles into one cell not just as a physical phenomenon, but as a computational necessity that aligns with the logic of a simulated universe. In this model, the universe's tendency to compress information acts like a force between particles, drawing them inward. It mimics gravity from the outside, but is actually a result of the universe's internal drive for informational order. According to Vopson, the greater the difference in information entropy between two particles, that is, the more orderly the system becomes when they unite, the stronger the attraction between them. Put differently, when the potential for entropy reduction is high, the force pulling the particles together is also strong. He formalizes this idea mathematically. This force is equal to the change in information entropy divided by the distance between the particles. This equation mirrors Newton's law of gravitation, which states that force is proportional to mass and inversely proportional to the square of the distance. Vopson simplifies his information-based formula using physical constants, showing that it leads to the same mathematical structure as Newton's law. Thus, the greater the information imbalance and the shorter the distance, the stronger the pull, not because of mass, but because of information. Naturally, this theory has attracted various criticisms. One of the most common is that Vopson's assertion that information entropy decreases appears to contradict the second law of thermodynamics. Critics argue that he needs to explain how this idea aligns with the well-established principle that entropy tends to increase over time. Another major concern is that Vopson's theory does not integrate well with existing frameworks like quantum mechanics and general relativity. The uncertainty around how his model would mesh with these foundational theories pushes it outside the bounds of current scientific consensus. Additionally, the theory's reliance on the simulation hypothesis presents another challenge. Since simulations are inherently untestable, many scientists argue that any framework grounded in this idea cannot be considered a proper scientific theory. Given that testability is one of the core criteria for a scientific model, it is worth noting that Vopson does acknowledge in his paper the need for future testing. However, he offers no concrete method for how such a test might be conducted. For example, if it could be proven that information has mass, the rest of the theory might follow, but the crucial question remains: how would we measure such mass? One of the most puzzling elements of the paper is the use of Newtonian physics at Planck scale distances. From a physical perspective, this seems questionable. However, it appears Vopson's goal is not to claim that Newtonian gravity applies at quantum scales, but rather to demonstrate that his information-based model yields the same results in form. From my perspective, trying to explain gravitational attraction through information entropy and then link it to the simulation hypothesis feels overly speculative. Whether or not we're in a simulation doesn't really affect how we live day to day. In the end, simply existing in the process may be all that truly matters.